Welcome to the third of my little Haskell screencasts. In the last one we looked at infinite data structures, and I said something. I mentioned that infinite data structures, especially the cyclic infinite data structures, tend to be fragile, and care needs to be applied when using them in various ways. So today I want to look into that. So quick recap, and for that we'll go back to the GHCI interpreter. There were two kinds of infinite data structures we were looking at. Some were infinitely producing new values as you look at them. And an example of that might be the list starting from A all the way to all the Unicode characters, which is a pretty large list. And well, if I look at the first two elements, I get A and B. That's nice. So let's look at this data structure in memory. For that, we use ghgvis, which is a graphical tool to inspect the memory of a running Haskell program. And we can look at L1 and we see it contains of two const cells for A and B, which we've evaluated already, and then a thunk for everything else. And as we evaluate the thunk, we can do that by clicking here, we see that it'll slowly fill up our memory with more and more characters. In contrast, let's look at L2, which is the cyclic list built with from the list ABCD. And it starts with a thunk, so we can click on that. So it starts with A, and then the tail of that list is a thunk, and we get B, and we get C. And notice how this thunk keeps referring to the beginning of the list, which is useful, because once we're done, this points back to the beginning of the list, and now we have a cyclic list. So A, B, C, D, and then it points back to the beginning. And these kind of cyclic data structures are very nice because they allow you to express an infinite list in finite amount of memory without any thunks that are still to be evaluated. And you can do some fun things about them, but they are fragile. So what do I mean with that? Let's clear the view and only look at L2. So what are the things I can do with this list? Well, I could maybe index into it. So I can say L2 and then I look at the 10,000th element, and that's A, and that works fine. The indexing function, the double bang, just looks at the list and then infinitely goes through this loop of ABCD, not infinitely, but counting until 10,000, and then it finds that there's an A, and it preserves the structure of the infinite list. Now this wasn't really surprising. Haskell is immutable. Just looking at stuff doesn't change it. What about functions that take a list like this and return a list? Which one of these preserve this cyclicity in the sense that the resulting list is still cyclic? Well, there aren't actually that many that can do that. So one good example is drop. So if I look at L3 and I say that's drop 10,000 of L2, then the first two elements of L3 is AB. That's nice. Well, actually, let's use a different number. Let's use 10,002. So that's CD. And if I look at this in our view here, we notice that, well, actually, L3 really is just a pointer to one of the const cells that made up the original list. So L3 just points to this const cell. It is part of L2. So really, we're just pointing into the data structure. And these are the functions that you can apply to cyclic data structures without breaking the property if they return just a subcomponent, a substructure of that thing. Now for cyclic lists like this, there aren't many choices of functions that do that. There's indexing, because it just gives you an element in the list. And then there's all kinds of variations of take. So I can use take, I can use take while, and these give you an infinite list back that is still cyclic. What about drop? I meant drop. What about take? So let's look at L4 and let's take the first elements of L2. So L4 is just ABCD, AB. That's expected. And if you look at L4, we notice that it's actually larger than the original list. The original list had 1, 2, 3, 4 const cells and then a few characters. L4 actually has 1, 2, 3, 4, 5, 6 const cells. So as take goes through the original list, it unrolls it and creates a large list. And in that way, it breaks the property that the list is cyclic. Now, it's kind of unavoidable because the output of take 6 isn't cyclic. So it can't be a cyclic list. But what about functions that could be cyclic? What about the map function? So let's clear the viewer again, and let's define L5 as mapping the function to upper over L2. Now, this starts with AB as expected. And if you look at L5, well, we have A, we have B, the capital ones, and then we have a thunk. This thunk refers to a function. This function happens to be to upper. And it also refers to the next const cell of the original infinite list that it needs to look at. So if we go at that thunk, we get a const cell with 2 thunks. The first one is the application of the function to upper to the letter C. So clicking that should produce a capital C. And there it is. And then the other one is a thunk again that points to the next element in L2. And if I do that a few times, then I get D, and I get A, and I get B. And notice how we start still producing new const cells. So although we kind of know from looking at the code that after A, B, C, D, we could just start again with A and we could just point back here and get a cyclic list, it's not what we get. Because map doesn't know that the input is cyclic, so it'll just keep producing new const cells and doing something like indexing into the 10,000th of that list will easily fill up our memory. Now, could map do something better than that? Not in pure Haskell. So in pure Haskell, you can't behave differently based on how the values are represented in memory. All you get to do is look at their meaning, and you can't distinguish a cyclic list from a possibly infinite list that isn't cyclic. So in that sense, functions like map and also all the other functions like filter and other stuff that you might imagine would preserve the cyclicity of the input, they don't. And they really can't in pure Haskell. And that's what I meant last time when I said cyclic data structures are fragile. You have to be kind of careful what you do with them. And really there aren't just a few good patterns that you can use them with. Zipping is a good example, because then you usually don't use it right away. Now, is there really no way to have this cyclic map that preserves cyclicity? Well, there is if you look underneath the abstractions of Haskell and you reach for unsafe, dark internal features. And maybe we'll do that next time in this podcast. So until then, let me know what you want to hear about, what you liked, and see you next time. Goodbye.